All right, welcome. Today, we're basically becoming detectives. Our mission? To measure something totally invisible, something you can't see or touch, but that's running the show inside every single electronic device you own. I'm talking about electrical resistance, and we've got the perfect old school tool for the job.
So here's our game plan. We'll start with the mission, get to know our tool, build the circuit, then go on the hunt for the key piece of data. Crunch the numbers to find our answer, and finally, I'll give you some pro tips to make sure your results are spot on.
First things first, the mission. We've got this unassuming piece of wire right here, but don't let it fool you. It has a secret, a hidden property. It's resistance. And our job is to figure out exactly what that number is. And that right there is the big question, isn't it? I mean, resistance isn't like length. You can't just take a ruler to it. It's this invisible force that pushes back against electricity. So how in the world do we actually measure it? How do we make the invisible visible? Well, to do that, you need a very special instrument. So let's meet the star of our show, the meter bridge. It might look simple, but it's an incredibly clever device designed for exactly this kind of electrical detective work. So what exactly is a meter bridge? You can think of it as a physical, real-world version of a brilliant idea called a Wheatstone bridge. Its entire purpose in life is to find the unknown resistance of a conductor, and to do it with amazing precision. Okay, now this diagram, this is our treasure map for the entire experiment. Take a good look. See that long wire stretched across the bottom? That's the 1-meter wire that gives the bridge its name. Up top, you've got 2 gaps. That's where our known and unknown resistances will go. And right in the middle, you see the galvanometer. This layout is the key to everything. You know, the secret sauce here is the Wheatstone bridge principle. The best way to think about it is like a perfectly balanced scale. You have 2 sides of the circuit, and when the resistance ratios on both sides are identical, the bridge is balanced. And what happens then? 0 current flows through that galvanometer in the middle. We're looking for a perfect 0, a null point. This is so much more accurate than just reading a meter, because 0 is absolute. You can't get more precise than that. All right, enough theory. It's time to actually build this thing. This part is absolutely crucial because even one loose connection can throw our entire measurement off. So let's gear up. Okay, let's walk through it just like our map showed us. First, our mystery wire, we'll call it X, gets connected in the right-hand gap. In the left gap, we hook up a resistance box, we'll call it R. This is great because we know exactly what its resistance is. Then, our super sensitive current detector, the galvanometer, connects from the middle out to a little sliding pointer called a jockey. And finally, we connect our power source to the 2 ends of that long meter wire. And now for the best part, the most interactive, hands-on bit of the whole experiment. All that careful setup leads us to this moment, the hunt for the null point. This is where the magic happens. So what are we looking for? It's simple. We have one goal and one goal only. Find the null point. And what is that exactly? Well, it's that one magical spot on the wire where our electrical balancing scale is perfectly level. When we hit that point, the galvanometer needle will stop deflecting and point straight to 0. That tells us that absolutely no current is flowing through the middle of our bridge. It's perfectly balanced. So, how do we find it? First, a quick check. Touch the jockey to the far left end of the wire. See which way the needle kicks. Now, touch it to the far right end. The needle has to kick in the opposite direction. If it does, you're golden. It means the null point is hiding somewhere in between. Then you just gently slide that jockey along the wire, watching the needle the whole time, until you find the exact spot where it lands on 0. That's it. That's your balancing length. We did it! We found our null point, and we've got our balancing length written down. Now it's time to head back to the lab bench, do a little math, and finally reveal the secret of our mystery wire. And this elegant little formula is how we crack the code. It says our unknown resistance, X, is simply our known resistance, R, multiplied by a ratio of the 2 lengths of the wire. So if our balancing length is L, the rest of the wire is just 100 minus L. It's that simple. This works because the wire is uniform, so its resistance is directly proportional to its length. Pretty neat, huh? Now, a good scientist never trusts just one measurement, right? To be really sure, we have to do it a few times. So we'll change the known resistance R from our box, find a new balancing length L, and calculate X again. As you can see in the table, we do this a few times, then we can average our results to get a much more reliable answer. So, after taking our readings, calculating X for each one, and taking the average of all our results, there it is, the big reveal. For this wire, the unknown resistance is 2.68 ohms. Mission accomplished. But hold on, we're not quite done. Following the steps is one thing, but getting a truly perfect result, that takes a little finesse. So let me share a few pro tips to take your experiment from good to great. First, your connections must be tight and clean. Seriously, a loose connection adds its own resistance and can mess everything up. Make sure all the plugs in the resistance box are pushed in firmly. And when you move the jockey, be gentle. Don't scrape it along the wire, because that could change its thickness. Also, only turn the power on right when you're looking for the null point. Leaving it on heats up the wire and changes its resistance. And finally, here's the real pro move. Try to pick a known resistance R that gives you a null point somewhere in the middle of the wire, say between 30 and 70 centimeters. That's where the instrument is most sensitive. So we did it. We found the resistance of this specific piece of wire. But think about this for a second. That number depends on how long and thick this wire is. The deeper question, the much more interesting question, is what is this wire actually made of? What's its specific resistance? That's a fundamental property of the material itself, and with the number we just found, we're one huge step closer to figuring that out. So what do you think the next step is?